Hello and welcome to Future Path. I'm Americo Forestieri, Director of External Affairs at the NASA Lewis Research Center in Cleveland, Ohio. In NASA's goals to try to fly higher, further, and faster, new materials and structures are required to meet these goals. In today's segment, we're going to look at some of the things being done in our Structures Division on structures for flight propulsion. I think you'll find it interesting. Let's watch.
Flight, in the air or in space, requires propulsion systems able to withstand extremes of mechanical stress, vibration, and temperatures. Designing these structures and matching available materials to the job has always been a complicated business, and is becoming more so. Requiring safety and reliability from structures needing minimum maintenance, having the least possible weight, poses a basic contradiction which can be resolved only by the most sophisticated analytic methods. The Lewis Research Structures Division is dedicated to advancing the state-of-the-art of structures technology for aeronautical, space, and terrestrial applications. The principal product of the division is the development of validated analytic methods to predict the behavior of structural components and systems for aerospace propulsion and power machinery. Division provides not only solutions to problems encountered in current applications, but also leadership in setting new directions for structures engineering to solve tomorrow's problems today.
The purpose of the Structures Division at Lewis Research Center is to develop advanced, credible design tools. These tools can then be used by designers to design advanced concepts for future missions, both in aeronautics and in space. We develop these methods for use on high-speed computers, and they are validated with state-of-the-art laboratory equipment. We can predict the life, that is, the number of missions that can be flown by the advanced concept, and we can optimize the design, both from the point of view of minimum weight or from the point of view of lowest cost.
Breakthroughs in flight usually follow developments in propulsion systems. In the early days of flight, structures design was a combination of art and trial and error. If you were developing a rocket, you built an engine derived from earlier designs. To be sure it didn't fail, you made it sturdier, heavier. As technology advanced, lighter, stronger materials and improved manufacturing methods made the impossible possible. But mistakes were still made, and the results were spectacular and costly failures. The job of the Structures Division is to make sure such accidents will no longer occur. They do this by applying the latest scientific analysis possible and by using the most up-to-date testing equipment and methods available. To do this, the staff of scientists, engineers, and technicians of the division perform work in structural mechanics, structural dynamics, fatigue, fracture, and on projects and applications. Some of the work in structural mechanics includes characterizing the properties of metals used in propulsion systems. By subjecting specimens to stress and varying temperatures, researchers can predict maximum loading and operating temperatures. And testing is performed at very high temperatures on materials that will be used at places like the leading edge of the National Aerospace Plane Cowl. The work in structural dynamics focuses on the forces affecting bodies in motion. When the turbine in a jet engine loses a blade, or even during a very hard landing, the vibrations that occur can cause a propulsion system to fail. Tests in dynamics can simulate a blade loss condition to provide test data to compare with simulation models. Any rotating machine will tend to vibrate at certain critical speeds. And since modern rotating equipment is required to operate at ever higher speeds, this problem is increasingly important. Research in the division is developing methods for both active feedback and passive suppression to permit operation of equipment above critical speeds and to reduce bearing wear. High-speed computer simulation is required for the full dynamic analysis of rotating machinery. Parallel computing, developed in the division, is making this possible. By combining a large number of processors in one transputer, computations can be performed rapidly enough to study high-speed vibrations of rotating components. Studies in fatigue and fracture analysis are performed in many of the Structures Division's labs. Both destructive and non-destructive methods are used to evaluate and characterize new materials. And sometimes a combination of both are used to improve the analytical process. Much of this work is directed toward characterizing and understanding advanced material systems. As an example, researchers in the division sonic map a ceramic disc and send the data to a computer. The computer outputs a color simulation showing variations in density, defining areas where fractures should occur. Later, the disc is placed in a hydrostatic chamber and fractured. The actual fractured disc is then compared to the computer model for verification. Division researchers also test advanced fiber-reinforced composite materials under varied loads expected in aerospace applications. Data collected from these tests are used to verify mathematical models which describe the material behavior. These models are then incorporated into NASA computer codes and used to predict the performance of composite structures in a variety of applications. Beyond solving the problems which can lead to failures, the division provides leadership in developing new concepts and integrating information from many sources for application in areas ranging from windmills to the space shuttle main engines, from fuel-efficient propellers to computer codes for production design and propulsion systems simulations. The work of the division provides verified mathematical models and computer codes that are key elements of today's computer-based design analyses for flight propulsion systems, as well as many other systems with similar problems. Using the products of the Structures Division, designers can better predict the life of a component by constructing it on the computer, thereby saving time and material while preventing costly failure.
Future aerospace systems will require advanced capability. Onboard computation and real-time sensors will combine to make it possible to monitor the health of advanced systems. Active elements could be included to make it possible to suppress dynamic instabilities. Structural tailoring to account for local stresses and local hotspots may be the only way to take advantage of the new lightweight, high-temperature, yet very brittle materials. Computational simulation will allow designers to make rapid, affordable, and feasible designs. Probabilistic methods will allow designers to quantify risk and make trade-offs between performance and life. Combination of these capabilities will allow those designers to operate and design closer to the limits. Such capability will allow us to build systems that we couldn't build before, to carry out missions that conceivably couldn't be carried out with the development of these capabilities. The Structures Division hopes to play a major part in bringing them about.
The special combination of experienced, in-house staff and facilities in the Lewis Research Structures Division has been tailored to meet the challenges and needs of the new age of spaceflight and aviation. The work of the division continues to evolve technology and will take us into the next generations of flight.
Our second segment is about a process developed at Lewis that we're very proud of. An engineer in our materials division developed a process called arc sprayed monotape. Let's find out about it and some of its many uses.
Unfazed by extreme fire-hot temperatures, possessing amazing strength, a strength beyond belief. Its creation, one of outstanding engineering achievement, the ultra-advanced composite materials being developed by NASA Lewis Research Center in Cleveland, Ohio. To understand this fascinating field, we must start with basics and determine exactly what is a composite material. Possibly the easiest way to visualize a composite material is to offer the example of a tennis racket. The arm and frame part of the racket is made by combining two distinct materials, graphite fibers, which give it strength, and a low-temperature glue or binder, which hold the fibers together and allows it to be fashioned into shape. This is a composite material. Two different parts, each with a different function. Research in this area began about 25 years ago, when minute whiskers were discovered growing on electrical devices. The whiskers were found to be single-grain crystals that, when tested, proved to be very strong. In later research work, the whiskers were used in the making of bulk materials. Today, instead of whiskers, fibers like silicon carbide, tungsten, and graphite are used with a glue or binder to make such things as engineering and sports products. There are some products, though, that need to be able to withstand higher temperatures. At the same time, it's also necessary that they be lightweight and stiff, which, incidentally, are very important requirements for just about anything intended for use in space. To meet the more demanding requirements, a glue or binder such as aluminum or titanium may be used. For other products that need to be heat resistant at even higher temperatures, a nickel or iron-based alloy is combined with either certain carbide fibers or tungsten fibers. There are several ways to do this, and one of them is the arc spray process. This method was developed right here at NASA by one of our engineers, Leonard Westphal. He works in the Advanced Metallics branch of NASA's Materials Division. Recently, Mr. Westphal described exactly how the arc process works.
The process works like this. We have an arc spray gun which is attached to a large vacuum chamber. Inside the vacuum chamber is a drum that has our real strong fibers wound on the surface at a very regular spacing. The arc spray gun works by having two metal wires coming into the gun, and an electric arc is struck between the tips of the wires. The electric arc has sufficient intensity to cause the wire tips to melt. A high pressure stream of neutral gas, and we usually use argon, very clean argon, is sprayed on the molten wire tips, causing the molten metal to dislodge from the wires and to be vaporized into very, very fine particles and sprayed, and we aim it right on this drum surface. The thin sheet that's formed can be as big as the drum surface.
The thin sheet Mr. Westphal was talking about is called a monotape. It comes off the drum very easily because a Teflon spray is applied first. The spray allows the material to get hard and yet not stick to the drum. It simply peels off. Composite monotapes are used to make composite shapes, which are rather complex structures requiring extremely high strength. In order to make the structure as strong as possible, the monotapes must be positioned in certain directions. To do this, the monotape is cut into small pieces and stacked one on top of the other. On the first piece, all fibers are placed in one direction. On the next piece, the fibers are put in the opposite direction of those on the first piece. This alternation of the fiber's direction is continued on the pieces in order to maximize the structure's strength in different directions. The small pieces of composite monotape usually are glued together by a method called hot pressing. Very heavy pressure is applied to the stack while it is subjected to a temperature of almost 2,000 degrees Fahrenheit. As the metal gets squeezed together, any small imperfections in the monotape disappear and the metal pieces blend together, resulting in a perfectly solid plate. Cut into thin strips, the plates are used extensively at NASA for testing purposes. Engineers have been able to make large tubes by using a pressing guide to shape it. They have made demonstration turbine blades for jet engines. These blades are located very close to the place where air mixed with fuel is burned. As combustion takes place, the expanding gases hit the blade, causing it to turn. It's easy to see why the blades must be able to withstand extremely high temperatures. Presently, there are 5 NASA programs in which arc spray monotape plays a major role. 2 programs deal specifically with the Space Shuttle's main engine. Since the material now used to make the main engine is cracking due to thermoshock, NASA is working with tungsten-reinforced superalloys to replace it. These composites, in tests so far, have proven to be more shock-resistant, stronger, and able to withstand higher temperatures than the present material. The second program deals with the reinforcement of a combustion liner in the Space Shuttle. Mr. Westphal explains.
A combustion liner is a contoured shape that is liquid hydrogen cooled, and it's the vessel that the liquid oxygen and liquid hydrogen burn in. And you have very, very high temperatures inside this combustion liner, and typically it's made out of copper or a strong copper alloy. The problem this combustion liner is experiencing is the copper alloy is deforming due to the very high temperatures and the stresses that are generated in the thin inner wall, causing the inner wall to deform and actually crack, and the liquid hydrogen is leaking out. We are putting tungsten fibers in the inside layer of the combustion liner to selectively strengthen the inner wall of the combustion liner. This is an example of one of the test specimens that we make, and we have tungsten fibers reinforcing the inside surface of this specimen. All right, this specimen then will be tested in a rocket test chamber under conditions very, very similar to the Space Shuttle main engine, and the material will be tested to failure. We predict a much longer life with our tungsten reinforced copper than the current copper alloy that's being flown in the Space Shuttle today.
Also regarding space, the third program has to do with the creation and development of very strong tubes to hold liquid metals and heat pipes for nuclear reactors. Because of the tremendous pressure the tubes will have to withstand, a new material is needed that is much stronger than the one now used. Using the composite process, engineers are adding tungsten fibers to the present material to strengthen it. And again, in support of space power, the next program is working to develop a specific container that will be able to take high temperatures and amounts of pressure which the current container cannot. In this case, the power being generated would be for a space station. The composite material that has been developed is 3 to 4 times stronger than the present one, surpassing the program's goal of finding a substitute container for present temperature and pressure levels. The engineers at NASA have created one that can be used as power demands go up in the future. The final program developing composite materials for use in space deals with the improvement of radiators. Again, NASA engineer Leonard Westphal explains.
These tubes I talked about before have radiator panels hooked on the back of them to get rid of the heat. All right. We're developing fiber-reinforced radiator panels that are made out of graphite fibers that have very, very high thermoconductivities. And thermoconductivity is the material's ability to conduct heat very quickly. All right, these fibers conduct heat extremely fast, and we put them in copper as a high-temperature glue. Copper also has very high thermoconductivity. And so what we end up with is a structure that has higher thermoconductivity than copper, is very, very stiff and light. And this saves weight, it increases the efficiency of the radiator panels, and makes the whole cooling scheme work much, much better.
At NASA, there is also very exciting work being done to support the National Aerospace Plane. The plans for this remarkable plane call for it to take off from the ground and fly up, right into orbit. It would fly like an airplane, but its jet engine, at higher altitudes and speeds, would become like a rocket and boost it into space. NASA's Advanced Metallics Branch is working on developing a fiber-reinforced inner metallic material out of which to build the plane. Currently, the plane severely lacks a suitable material. There are 3 vital requirements that the material must have. It must be lightweight, highly resistant to extreme heat, and very strong. Since it will be used primarily as a major structural component, the composite material being tested and developed uses ceramic fibers. The inner metallic matrix and ceramic fibers together form a material that could be the solution to one of the plane's most pressing needs. In all the research, in all of these programs, with all of the discoveries, breakthroughs, and amazing new products tested, and those actually in use, still, according to Mr. Westphal, the present work is, quote, just scratching the surface in composite materials. Besides the fibers in existence today, there are many, many others with great potential that need to be developed and tested. NASA's goal? To develop even stronger fibers that can work at even higher temperatures.
Some of the structures NASA has been working on will be used for the National Aerospace Plane, or commonly known as NASP. NASP, when it is built, will have the unique capability of taking off from any airport and fly directly into space. Let's learn more about NASP.
Imagine taking off from an airport runway flying at 3 to 5 times the speed of sound, at altitudes of 20 miles or even higher. A few short hours after departure, you come to a stop halfway around the world. Or maybe you took off from a runway and flew directly into orbit to work in space, and then you return, landing on a conventional airport runway. The National Aerospace Plane will try to make both scenarios a reality. NASA and the Department of Defense have done research on hypersonic technology for many years. The NASP technology demonstrator will be a highly advanced X-plane, a new member of the elite special research aircraft that includes the X-1, which in 1947 was the first aircraft to break the speed of sound and fly supersonic. In the early 1960s, the X-15 became one of the first manned hypersonic aircraft and reached speeds of Mach 7, or about 4,500 miles per hour. One of the key technological developments of the X-30, or NASP, are in the propulsion area. An air-breathing, hydrogen-fueled supersonic combustion ramjet engine, or scramjet engine, is now being developed for speeds from about Mach 7 to Mach 25. The engine uses the velocity of the vehicle to compress air as it is rammed into the intake. This compressed air is then mixed with gaseous hydrogen at this stage to generate high thrust. A development on which we will focus is materials. Here to speak on that is Matt Mellis.
With the advent of the aerospace plane, there's become a need for a lot of new material development. Beyond a shadow of a doubt, we need new materials, all right? And these new materials will most probably be composite materials, but instead of using a metal matrix-based composite, we'll be using, or epoxy-based, we'll be using a metal matrix-based composite, all right? Metal matrix being copper, for instance.
One of the big problems NASA is facing with the advent of the National Aerospace Plane deals with not only finding the right materials to use, but in cooling them as well.
We have to figure out some way of making a very strong material that's going to survive in a high temperature environment. And what we're going to have to do is actively cool this material, all right, by putting some kind of a cryogenic fluid behind it, gaseous hydrogen or liquid hydrogen, which is very cold, and acts as a good heat transfer medium to take heat away from the leading edge. So on one side of the material, on the inside of the wing, for instance, there'll be a lot of coolant rushing through to cool the inside down, and on the outside you'll have a very hot surface, and that is why we need the high heat conductivity. For instance, you look at fighter jets that travel Mach 1 or Mach 2, or even the Concorde, which goes up to Mach 2. you see that their wings are very narrow at the leading edges, okay? And there's a problem with that because the smaller the leading edge gets, the more difficult it is to cool, and the hotter it gets because it's such a small, it's just such a small point lying out there in the free stream that it gets very warm very quickly.
The National Aerospace Plane is one of the projects being developed by NASA for future space use. But we cannot expect it to do all of our work in space.
The National Aerospace Plane being something that will possibly be able to supplement the shuttle fleet or maybe even replace it. But obviously, if you have an airplane that can take off from a runway and go to orbit with some people in it and go to the space station, for instance, or something like that, obviously it would be capable of shuttle-type operations. As far as payload goes, I think moving big things like space station components, or say, for instance, they want to go to Mars, and they have to get some big boosters up there or something like that. I don't see the National Aerospace Plane taking that kind of payload up there.
The National Aerospace Plane is expected to yield a high payoff for the United States in the early 21st century with reduced space launch costs, vastly reduced transit time on long-haul air routes, major investments by private enterprise in commercial space ventures, and sustained U.S. preeminence in aeronautics, with all of the social and economic benefits that accompany it.
This is Americo Forestieri wishing you goodbye and hope you've enjoyed our show. I hope you'll walk along the future path again with me at NASA's Lewis Research Center in Cleveland, Ohio.